Okay, so looking at this one here, we have a sphere, and the sphere has a radius of A. So the radius of the sphere is A. That's the sphere. Now, looking at this also, if that's A along there, just be careful that you know that is also A there. X is the whole height of this cone, okay? And R equals the radius of the cone. I'm just going to change this to something a bit smaller. A is the radius of the sphere, so it also goes out there. In this question, you'll notice that this length here, down to here, and this length here, they're different lengths, they're not the same length. And then we have this triangle coming out here. Okay, so first of all, we're looking at the volume. So we need to find the volume V, but we need to get it all in terms of the variable, which is X. A is a constant. A is the radius of the sphere. R is a variable. So this is the cone that sits inside the sphere. Like if you had the sphere, the cone could possibly be that big. Or it could be really skinny like that. So it can actually change. The sphere stays constant, but the size of the cone changes. Okay, so first of all, the volume of the cone, that's what we're interested in, is 1/3 pi r squared h. So that's going to be 1/3 pi little r squared, and then the height of the cone is x. So the height equals x, and you see that's there. Okay, so what we need to do is we need to get r out of the picture, because r is not in here, it's in terms of x. So we need to find r in terms of x. So you can see the right angle triangle thing happening here. That's r, that's a, but we don't have this length here. So call that y, for example. So that's y there. So when you look at that size of that, you look at this, that whole thing there is x. This part here, that's what I'm trying to find. And just this part up the top there, that part up the top, it's a different colour, that one. Okay, that's equal to a, because it's the radius of the sphere. So if I just want y, which is this part here, it'd be x, which is the big thing, minus a. So y will actually be x minus a. So that means that I have the volume. That. So the volume is 1/3 pi r squared x. R we can get in terms of x by using this right angle triangle. So that's a, that's little r, and this is x minus a, because it's the big length of x, take away the little a there, which is the radius of the sphere, and that will give you this length here, which is y. So in that triangle, if I use Pythagoras, x minus a squared plus a squared equals, take that back, plus r squared equals a squared, because a squared is the bigger side. So we're trying to find r squared, because we want r squared. So r squared is a squared minus x minus a squared, because we want to get it all in terms of x. So we actually want to get rid of this r. Okay, so that's going to be a squared minus, this will be x squared minus 2xa plus a squared, which is a squared minus x squared plus 2xa minus a squared. So the a squareds cancel out, so it's minus x squared plus 2xa, which is equal to 2xa minus x squared. And if you factorize, it's x to a minus x. So that's basically what r squared is. So now if I take that and I sub it into my volume, that's 1/3 r squared. So that's x times 2a minus x times x, 1/3. So it's 1/3 pi x squared 2a minus x. Now our prize is 1/3 pi 2a x squared minus x cubed. So if I expand that section there, you get 1/3 pi 2ax squared minus x cubed when I do the second eyebrow on that. Okay, so that's as required. So the second part says find the value of x for which the volume of the cone is a maximum. So in order to do that, we're going to have to differentiate this. So we find b dash. So remember the constant out front, you can just multiply it, so you don't have to worry about that. And just differentiating this. Remember, a is just a number or a constant. So it's 2a times 2x, because the x is the variable, minus 3x squared. So it's 1/3 pi 4ax minus 3x squared. There is a common factor there of x, so it's 1/3 pi x 4a minus 3x. So the maximum and minimum occurs when b dash is 0. So 1/3 pi x 4a minus 3x is 0. 1/3 pi x would leave you with x is 0, and that's no solution, because if x is 0, there'd be no cone, because there's no height. 4a minus 3x is 0. 4a is 3x, so x is 4a over 3. Okay, so we have to check it is a maximum. So let's differentiate again. So this is what we're differentiating. I'm going to go back up to the other line actually, that one. Because we've got 1/3 pi, we'd rather that part was expanded. 4a, because the 4ax will just go to 4a. 4a is a number. 6x. So if I put in x is 4a on 3, b double dash is 1/3 pi 4a minus 6 times 4a on 3. So that'll be 1/3 pi 4a. 24 on 3 is 8a. So it's 1/3 pi minus 4a. So the most important thing you see here is that is less than 0. So therefore it is a maximum when x equals 4a on 3. So the question says to find the value of x for which is a maximum. So we've done that. And it's in terms of a, but remember a is a constant. So there's your solution. Okay. All right, so this one. So the diagram is a cylinder within a cone, given the volume of the cone, volume of the cylinder. All right, so let's just see what's happening here. When you get situations like this, I don't know exactly what's happening, but you can actually see how there is a similar triangle sitting in here. That's H. That is often what you use to get your relationship. So that's H and that's R. This is X. And see how they got the Y? That would be Y there. So when you're doing similar triangles, X on R will be the same as that one on the whole thing on H. So that one there, H is the big thing, Y is just the little one. So that'd be H minus Y. So you get X on R is H minus Y on big H. Now, I don't know how we're going to use this yet, but I'm just going to have a quick look. Okay. All right, so where are we with this? This one is, which one is it? It's question here. Just going to add a page in. All right, so the first part of the question, part 1, show that the volume of the cylinder is written by that. So that's my prize. So V is big H on little h, pi x squared, big R minus x. So what is the variables here? Okay, so the variables. So the diagram shows a cylinder XY inscribed in a cone of radius A and H. So the height, the R and the H of the cone, they are fixed. Okay, the actual cylinder that fits in there with a radius of X and a height of Y, they are variables. As you can see, as the cylinder changes height, then the X and the Y changes height within that cone. So we're interested here in the volume of the cylinder. So the volume of the cylinder is pi R squared H. So we need to get that all in terms of X, because if you look at the prize, this is the prize. The prize is V is h over r, that's constant, pi, x squared, then you got r minus x, they're the variables, the x's and the v. Okay, so we need to get the x is equal to, r is equal to the x, and the h, the height of the cylinder, is y. Okay, now we need to get it all in terms of x, so we need to get rid of the y. So if we go back up to what we did before, we had big H is the big one. This is big R. This is little x, and y is this little piece here. Okay, so we need that one there to match it because we need x2, that one would be h minus y. And if you look at the big one, it's big H, big R. So the relationship here would be h minus y on h equals x on r. Okay, so we're trying to get rid of the y. So let's go h minus y equals x on r times big H. Now I'd like to make that a positive y. So I'm actually going to bring that to that side. So it's x big H on r plus y. It just makes life a little bit easier. Then y equals big H minus x on h to r, because I can take this and move it to the other side. Okay, so what's going on now here? We have v r squared, x squared, h minus x h on r. And I'm just looking at my prize to see what I'm trying to get this split. We've got h on r pi r squared. Okay, so I can see from here, I can take out the h. And the other thing I need to do is get a common denominator. So that's going to be r, okay? 1 times r. So it's going to be r minus x on r, which is pi x squared h. And I'm going to pull this r out the front as a denominator. That's like having that on 1. And then it's r minus x. And I'm pretty sure if you have a good look at this now, that there, I think, is my prize. Let's just go back up. Yeah, the same thing. Okay, so all I've managed to do there really is do the formula part. So I found the formula. Now the second part says, by considering the inscribed cylinder of maximum volume, show that the volume of the cylinder does not exceed 4/9 of the volume of the cone. So volume of the cylinder is not bigger than 4/9 of the volume of the cone. Okay, if you want it to be the maximum. So maximum, that's V is pi h on big R. I'm going to put that x squared back in there. It's got to go r x squared minus x cubed. V dash is pi h on r 2rx minus 3x squared. Make V dash equal 0. Pi h on r 2rx minus 3x squared equals 0. That cancels out. 2rx minus 3x squared equals 0. Factorize out the x. So you've got 2r minus 3x equals 0. X can't be 0. 2r equals 3x. X is 2r on 3. Okay, so we've got x. Now what we need to do, we need to show that it is a maximum. So differentiate twice. You get pi h on r 2r, because that x will go, minus 6x. And x is 2r on 3. You get pi h on r, 2r minus 6 times 2r on 3. 3 goes into 6 twice. So you've got pi h on r, 2r minus 4r. Pi h on r minus 2r, because 2r minus 4r is minus 2r. Less than 0, therefore that's the maximum. Okay, so x is 2r on 3. That means the volume of the cylinder would be pi times, let's look at the volume of the cylinder, pi times h on r x squared minus x cubed. We want to see that this does not exceed the volume of the cone. So we put this in minus 2r on that cubed and we work that out. We need a bit more space. And the volume of the cone is 1/3 pi big R squared h. Okay, so this here is pi h on r. That's going to be 4r cubed on 9 minus 4r cubed on 27. Common denominator, the times 3 times 3. Pi h on r, 12r cubed minus 4r cubed on 27. All right, pi h, 27r, 8r cubed. So the r's will go out, so you get r squared. So it equals pi r squared h on 27 with an 8. So the cone is 1/3 times pi r squared h. The cylinder is 8 on 27 times pi r squared h. So we want to know that the cylinder doesn't exceed 4/9 of the cone. All right, so 4/9 of the cone. So there's the cone, that one there. What happens if we multiply that by 4/9? You will get 4 on 27 pi r squared h. Let me just see the 4/9 part here. I think I've done something minor. 4, that should be 4 pi r squared on 27, and that one's right. I've somehow got 8. Let me just check my working. Oh, I know why. Because that there, when you cube the 2, I should have got 8. So that's going to make that 8. So that's going to make that 4. Which will make that 4. Okay. Which will make that one 4. So the cone will be 4 on 27 pi r squared h, or 4/9 of that. And this will be 4 on 27 pi. So 4/9 of the cone is that, and the cylinder is that. So it does not exceed it. If I didn't make that clear, the cylinder, the volume is 4/27 pi r squared h. The cone is 1/3 pi r squared h. So 4/9 of the cone will be 4/27, which is the same as the cylinder. So it does not exceed it, it actually equals it. Okay. I think the only one we have now to do is